This video is for Section 5.3, Conditional Probability and Independence. The first thing we're going to talk about is conditional probability. So conditional probability is the probability that one event will happen given that another event has already happened. The probability that event B happens given that A has already happened is represented by this notation right here. So it looks like P, parenthesis, B, with a line, and then A, close your parenthesis. So what this means is B, given that A has already happened. So students at the University of New Harmony received 10,000 course grades last semester. The two-way table below breaks down these grades by which school of the university taught the course. The schools are liberal arts, engineering, and physical sciences, and health and human services. This table is based closely on grade distributions at an actual university, simplified a bit for clarity. College grades tend to be lower in engineering and physical sciences, EPS, than in liberal arts and social sciences, including health and human services. Consider the two events. E, the grade comes from an EPS course, and L, the grade is lower than a B. So for number one, we want to find the probability of L. Interpret this probability in context. So probability of L is the probability of a grade lower than a B. So grade lower than a B would be everything in this column. So what you would need to do is you would say 2268 plus 800 plus 588, which gives you a total of 3,656 out of 10,000 because there's 10,000 total. And so whenever you do 3,656 divided by 10,000, you get 0.3656. So I get the probability of L by saying adding up all of the below B's over the total of course grades that we have. 2 says find the probability of E given L and L given E. And so the first one means the grade comes from an EPS course given that it's lower than a B. And the second one is the grade is lower than a B given that it's from an EPS course. Then it asks us which of these conditional probabilities tells you whether this college's EPS students tend to earn lower grades than students in liberal arts and social sciences, and then explain. So the first thing we will do is find the probability that it's an EPS course given that the grade is lower than a B. In order to do that, you need to first find the probability that it's an EPS course and it's lower than a B. So whenever you have the probability of A given B, what you're going to do is start out by finding the probability of A and B at the same time over the probability of B. So what we have to do to start with is find the grades that are from an EPS course and are below a B. So that would be 800 because I go to my engineering and physical sciences and find the grades that are below a B, which is 800, over probability of L in this case, which is a grade lower than a B. And so we said grade lower than a B was this 3,656, so 3,656, because that's all of my lower than a B's added together. So if I were to divide that out, I would get 0.219. 0.219. And then I'm going to find the probability of L given E. And so I'm going to do the probability of L and E at the same time over the probability of E. So this is going to be grades that are lower than a B and from the EPS. And so we said that was going to be 800 because I would look at EPS and then lower than a B. And then probability of E is the probability that it's from an EPS course. So what I would need to do is find out how many grades are from an EPS course altogether, and I could find that by looking at this row and adding those numbers all up. So 368 plus 432 plus 800, and I get 1600. And so 800 over 1600, of course, would be 0.50 or 0.5. So the next question says, which of these conditional probabilities tells you whether the college's EPS students tend to earn lower grades than students in liberal arts and social sciences, and explain. So this gives the probability of getting a lower grade if the student is an engineer. We would want to compare that to the probability of getting a lower grade if the student was in liberal arts and social sciences to be able to truly answer that question. The next thing we're going to talk about is independent events. So two events where the occurrence of one event has no effect on the other, on the chance of the other event that will happen, those are independent events. So, for example, if we were testing independence, we could use the probability of A given B equals probability of A, and the probability of B given A equals the probability of B. So this is kind of the rule that we would need to check to see if two events were independent. So remember that this would mean the probability of A and B at the same time over the probability of B. And whenever we work that out, we would end up getting the probability of A. And then for this one, we would say probability of B given A would be probability of B and A at the same time over the probability of A. And when we worked that out, we would get probability of B. So these two situations have to be true in order for us to say that two events are independent. And so when one happens, it does not affect what happens with the second event. Hey.
I feel really bad about the jack-o'-lanterns.
Why?
Well, I mean, they're all over the place now, and they have these faces. You know, some of them look happy.
Right.
Some of them look angry.
Mm-hmm.
Some even sad. But I know that really they're all just empty inside.
That is so deep. Thank you for sharing that. Okay. I'm making a video for my class.
I'm sorry.
Welcome to my life. All right, for each chance process below, determine whether the events are independent and justify your answer. So for number one, we have to shuffle a standard deck of cards and then turn over the top card. Put it back on the deck, shuffle again, and then turn over the top card. Define events A as the first card is a heart and B as the second card is a heart. So for number one, we have to determine if these are independent or not. So if you think about it, independent means that whatever we do the first time does not affect what happens the second time. So whenever we shuffle this deck and we turn over the first card, the key is that we put that card back in the deck. And so because we put that card back in the deck, when we start with 52 cards. When we pull that top card and then we put it back in the deck, we still have 52 cards, which means that whatever we did for the first turn didn't affect the second turn. So in that case, event A and event B would be independent. Because even if we did get a heart for the first card, because we put that heart back and we shuffle again, it's not going to affect whether or not we get a heart for the second card. If we had taken the cards and we had shuffled them and we kept the first card, that would change the number in the deck to 51, which is going to change the probability of choosing a heart for the second card. 2 says shuffle a standard deck of cards, turn over the top 2 cards one at a time. Define event A, first card is the heart, and B, second card is a heart. Alright, so for number 2, because we have a standard deck of cards, we start with 52 cards. We're going to choose 2 of the cards. So basically, we take the 2 cards and we draw them at the same time. Whenever we draw those 2 cards, we're going to look at one card first, and then we're going to look at the second card. So the probability for the first one that we choose a heart, we know that there are 13 hearts in the deck, so the probability for the first one would be 13 out of 52. But because we chose that card and it wasn't in the deck when we picked up the second card, our probability for the second card, assuming that the first card was a heart, would be 12 out of 51. Because if you think about it, even though you pick these cards up at the same time, the one on top had more chance, there was more cards in the deck when you chose that first card than there was for the second card. So these are not independent. So you could think about it like this. Once we know the suit of the first card, then the probability of getting a heart on the second card will change depending on whatever the first card was. 3. The 28 students in Mr. Tabor's AP Statistics class completed a brief survey. One of the questions asked whether each student was right or left-handed. The two-way table summarizes the class data. Choose a student from the class at random. The events of interest are female and right-handed. So if you are thinking about choosing a person and you are specifically worried about their gender and whether or not they're right-handed, remember that independent means that one does not affect the other. And so for this one, being a female does not affect whether or not you are right-handed. So that means that these two events are independent. Once we know that the chosen person is a female, this does not tell us anything about whether she is right-handed or not. So if we look at the information that we have, we see that we have 21 females total. If we add all of those up, we see that 18 of them are right-handed. So 18 of those females are right-handed, but we see that total there are 24 people that are right-handed. And we see that there are a total of 28 people that we were worried about. We also see that up here. So overall, there are 24 out of 28 students that are right-handed. We could reduce that number down to 6 out of 7 are right-handed. And among the women, we see that there are 18 out of 21 that are right-handed. 18 out of 21, and that would also reduce to 6 out of 7. So what that means is the probability of being right-handed is equal to the probability of being right-handed given that you're female. We're going to talk about tree diagrams and the general multiplication rule next. So the tree diagrams in action. Let's return to Mr. Tabor's AP Statistics class from the preceding. Check your understanding. The two-way table showing the gender and handedness of the students in the class is repeated below. So the first thing that we have to do is suppose that we choose 2 students at random and draw a tree diagram that shows this sample space for this chance process. All right, so for A, we start by randomly selecting a student. So when we randomly select a student, we see that there are 4 out of the total 28 that are left-handed. So the probability that the first student is left-handed is 4 out of 28. Let me move this down a little bit so I've got enough room. All right. This is for the first student. All right. If the first student was left-handed, let's say the second person is also left-handed, there would be 3 out of 27 that was probability of choosing the second left-handed given the first was also left-handed. And that probability is 3 out of 27. So if you notice, the number of people that were left-handed went down by 1 because we assumed that the first person was left-handed. And of course, the total number would go down by 1 to 27 because it's kind of like we took that left-handed person out of the pot. All right. We can also tell that there are 24 people that are right-handed. So let's assume that the first person was left-handed, but then the second person is right-handed. So this is left and then right. So if we think about that, there would be 24 people that were right-handed out of 27 people because we assumed that the first person was left-handed. So the probability the second is right given the first was left is going to be equal to 24 out of 27. All right, let's assume, though, that the first person is right-handed. So the first person is right-handed, there's 24 out of 28. Probability first is right. 24 out of 28. My dishwasher is draining, so if you can hear water running, that's what's happening. All right, so this is right. All right, then let's say that from there, the second person is left-handed. So the number of left-handed people is 4 out of 27, based on the fact that we have taken the first person that we assume is right out of the pot. So 4 people total are left-handed, 27 people total because we took out one person that was right-handed. So the probability that the second is left, given the first was right, is going to be equal to 4 out of 27. But let's say the first person was right-handed and the second person was also right-handed. So because there were 24 out of 28 for the first person, if that person was right-handed, the chances of the second person being right-handed would be 23 out of 27, because we would take one away from being right, which would change the total number down at the bottom to 27. And so the probability that the second is right, given the first was right, is going to be 23 out of 27. So for B, we want to find the probability that both students are left-handed. All right, so what this means is that we are going to find the probability that the first is left, and the second is also left. What that's going to look like is probability of left times the probability of left given left. Now the reason that this one is left given left is because we have to worry about taking out the first person from being left and from also the total number of students. So what that's going to look like is probability of being left is 4 out of 28. Probability of being the second being left given that the first was left, so this is second left given first was left. We said that that would be 3 out of 27. I have to multiply because it's an and. And so whenever I do that, I would get 12 out of 28 times 27, 756. And so 12 out of 756 would give me essentially 0.016. The general multiplication rule. So the probability that events A and B both occur can be found using the multiplication rule, the general multiplication rule, which says basically what we just did in the last problem. So the probability of A and B is equal to the probability of A times the probability of B given A, where the probability of B given A is the conditional probability that event B occurs given that event A has already occurred. So check your understanding. A computer company makes desktops and laptop computers at factories in 3 states, California, Texas, and New York. The California factory produces 40% of the company's computers. The Texas factory makes 25%. The remaining 35% are manufactured in New York. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70% and 50% respectively are laptops. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center. The first thing we have to do is construct a tree diagram to represent this situation. All right, so to begin, we're talking about computers. And we have 3 different places that they could come from. So the first one is that it comes from California. The second one is that it comes from Texas. Let's do this. California, Texas, and New York. All right, so the probability that it comes from California is 0.4. I got that from here. The probability it comes from Texas is 0.25, and the probability it comes from New York is 0.35. All right, each one of these states makes laptops and desktops. So I'm going to split these up to laptops, desktops. And so each one gets those branches. All right, so other computers made in California, 75% are laptops. So right here would be 0.75. Of those made in Texas and New York, 70% are laptops from Texas, and 50% are laptops from New York. All computers are first shipped to a distribution center in Missouri before being sent out to stores. All right, so if you think about the probability that you are in California and are a desktop, because 75% of them are laptops, would be 0.25. So given that same logic, if you had 70% that were laptops in Texas, then 30% would be desktops in Texas. And if you have 50% that are laptops in New York, then you would have 50% that are laptops desktops in New York. And so if you notice, each one of these adds up to be one whole, because you either have to be a laptop or a desktop. All right, so probability that you are a laptop from California, you would say 0.4 times 0.75. So 0.4 times 0.75 to get 0.3. So the probability that, chosen at random, a laptop from California, you would say probability that's from California, 0.4 times probability it's a laptop, 0.75 to get 0.30. So given that same method, we would say to be a desktop from California, you would say probability it's a desktop, or it's from California, is 0.4 times probability that it's a desktop, 0.25. Basically what we just did is probability that you're from California and desktop, which if you think about it is probability from California times probability of being a desktop. That's the basic probability stuff we talked about the other day. So 0.4 times 0.25. 0.1. From being from Texas and being a laptop would be probability of being from Texas and a laptop, which would be 0.25 times 0.70. Which would be 0.175. From being from Texas and being a desktop, if you work that out, would be 0.075. Probability of being from New York and being a laptop would be 0.35 times 0.5, which would give you 0.175. Being from New York and being a desktop would be 0.35 times 0.5, which would also give you 0.175. Number 2 says find the probability that the computer is a laptop and show your work. All right, so this one is a little different. So the probability that you choose a laptop. remember that those laptops can be from California, Texas, or New York. So what we're going to do is say probability of being a laptop and from California. I'm going to add to it this time the probability of being a laptop and from Texas, and the probability of being a laptop and from New York. So we said the probability of being a laptop from California, 0.30, plus probability of being a laptop from Texas, we said was 0.175, and the probability of being a laptop from New York, we said was also 0.175. So what we would do is say 0.3 plus 0.175 plus 0.175 to get 0.65. So 0.65 would be the probability that the laptop, or that the computer is a laptop. Essentially what we did on this one is probability of being a laptop. You could be a laptop from California or Texas or New York. So this is an or type situation. So this is like, this would be equal to probability that you are from California or Texas or New York. And because you can't be from California, Texas, and New York at the same time, we didn't have to subtract out anything where they would overlap. This is sort of like what we did the other day when we talked about basic probability. We just didn't have to worry about the part where they were overlap because you can't be from all three of those places at one time, or any two of those places from one time. Multiplication rule for independent events. If A and B are independent events, remember we said that independent events meant that one doesn't affect the other one. Then the probability that A and B both occur is probability of A and B, which is probability of A times probability of B. So for number 1, it says, during World War II, the British found that the probability that a bomber is lost to enemy action on a mission over occupied Europe was 0.05. Assuming that missions are independent, find the probability that a bomber returned safely from 20 missions. So for number 1, the probability that one returned safely would basically be 1 whole minus 0.05. And that's because in our problem it said that the probability that a bomber is lost through enemy action was 0.05. And so if we say 1 minus 0.05, we would get 0.95 that it returned safely. So if we assume independence, that means that one is not going to affect the other one. So that would mean that we would have 0.95 20 times. So that would look like probability that a safe return on 20 missions would basically be 0.95 times itself 20 different times, because it would be like saying the probability of A times the probability of B, which means that it was safe, times it again and again and again and again. So this is basically 0.95 to the 20th power, which would end up being 0.3585. Two, government data shows that 8% of adults are full-time college students and that 30% of adults are age 55 or older. Since 0.08 times 0.34 equals 0.024, we can conclude that 2.4% of adults are college students or older. Why or why not? So if you think about that, we would not be able to conclude that that was true because whether one is a college student and one's age are not independent events. Far more younger people than older people are college students. So we can't just assume that based on these statistics that 2.4% of adults are college age or college students 55 or older. Conditional probability formula. To find the conditional probability of B given A, we're going to use the formula that we sort of talked about earlier. So, who reads the paper? In Section 5.2, we classified the residents of a large apartment complex based on the events A reads the USA Today and B reads the New York Times. We then completed the Venn diagram and it's reproduced here below. What's the probability that a randomly selected resident who So using the formula that we had on the last page, which was probability of B given A, we would say the probability of A and B at the same time over the probability of A. So we know that A and B at the same time means that they read both of the papers, which based on our Venn diagram would be 0.05, and the probability of A is that they read the USA Today, which is going to be 0.40. The reason it's 0.40 is because we have to include that 5% where they also read the New York Times. So we have to say 35% plus 5% makes 40%. So 0.05 divided by 0.40 gives us 0.125. So the probability that a randomly selected resident who reads the USA Today also reads the New York Times is 0.125. Which means that there's a 12.5% chance that a randomly selected resident who reads USA Today also reads New York Times.